Today, we're going to analyze this circuit, which includes a transformer. So as you can see, we have that voltage forcing function sine of 2t plugged into this network of resistors, capacitors, inductors, and a transformer right here in the middle. And the transformer has a turn ratio of the secondary turns to the primary turns of 2. And our goal in this circuit is we would like to solve for the voltage at this corner node right there. Let's call this, let's call it V2. So how can we go about finding V2 and specifically the steady state solution for V2? Well, first of all, let's go ahead and convert all the components of this circuit into the phasor domain. So for example, this resistor here, resistors are equal to themselves in the phasor domain. So this resistor is 1 ohm, so it's just gonna have a value of 1. What about this capacitor? Well, we know capacitors in the phasor domain are governed by this formula, 1 over j omega c. Here, omega is the angular frequency, which is omega is 2 from this forcing function. And the capacitance here is 1 farad, so we're plugging in 2 here and 1 here. So we're left with 1 over 2j. That's going to be this capacitor in the phasor domain. Let's put that in. 1 over 2j. I'm going to leave this transformer alone. We'll deal with that in a minute. The inductors are governed by the equation j omega L in the phasor domain. Again, omega here is 2 from this forcing function, and the inductance is 1 Henry, so this is 1. So this just becomes 2j in the phasor domain. And this resistor, of course, also just stays at 2. We're going to remember that turn ratio N2 over N1 is 2. And then the last thing we want to do is we actually want, we also need to take care of that forcing function. So we know that if we have a cosine of omega t plus theta in the time domain, this will become a e to the j theta in the phasor domain. So how can we convert sine to cosine? Well, it always helps me to draw out a picture. So I know that cosine looks like this, and I know that sine looks something like that, sine waves versus cosine waves. And so I know that if I want to represent sine as cosine, then what do I have to do to this cosine function to shift it over to be a sine function? Well, I'm going to have to shift it over by 1/4 of a period, which is pi halves. And specifically, I'm going to have to do, I'm going to say that sine of some angle, let's just call it angle theta, is going to be cosine shifted to the right by 1/4 of a period, or pi halves. And counterintuitively, that's a minus sign there. So that's what that will look like. And if we apply that to this forcing function here, I know that sine of 2t is then going to equal cosine of 2t minus pi halves. So now I can apply this phasor formula here. So if this has an amplitude of 1, then I can say in the phasor domain, this forcing function right here, this will equal the magnitude of 1 e to the j, and what is this, j e to the j theta? What was this offset here? That's negative pi halves. Perfect. And then also, if I just look at e to the j times negative pi halves, I can simplify that, of course. So we know that in general, e to the j, where j is the imaginary unit of, let's call it alpha, is generally equal to cosine alpha plus j sine alpha. So if I let alpha equal negative pi halves, then this is going to be cosine of negative pi halves plus sine of negative pi halves? Well, this is going to be 0, because think about negative pi halves on the unit circle. What angle does that make? Its x-coordinate is going to be 0, and its y-coordinate is going to be negative 1. So this whole shebang is just going to equal j times negative 1, or negative j. So my whole forcing function, this is just going to become negative j. It's pretty simple and nice. So my whole forcing function is just negative, the negative imaginary unit. Okay, perfect. Now, how can I go ahead and deal with this transformer in the middle of this circuit here? And the way that we normally do that is we are actually going to take the impedance that we see on that side of the circuit, and we're going to shift it over to this side of the circuit, move this all the way over here, and we're going to manipulate its value so that the whole circuit will be sort of equivalent to what it once was, but it will have the effect of getting rid of this transformer, these transformer coils in the middle here. But how can we shift impedance from this side of the circuit through these transformers to this side of the circuit? Well, don't memorize the formula for it. Just rederive it yourself from first principles. So let's say we have some forcing function here. We have some complex impedance here. We have some transformer with a turn ratio N1 to N2 there. And then we have some complex impedance there. Then let's say that we have current here be I1, current here be I2, current here, not current here. I want the voltage up top here to be V1, and I want the voltage here to be V2. And of course, this is all happening in the phasor domain. So now let's just write some equations and see where they lead us. So I know that the current in this branch of the circuit, let's say I1, is going to be the voltage here, which is F, minus the voltage here, which is V1, all over the impedance right there, which is complex number Z1. Again, we're all in the phasor domain. And similarly, I know that the current here, I2, in that second branch of the circuit, is going to be the voltage here, which is V2, minus the voltage here, which this is grounded, so 0, all over the complex impedance there, which is Z2. And then let's think about the first principles of transformers themselves. So transformers, what do? Well, they make sure that the voltage across the transformers, or between both sides of the circuit, stay in the same ratio as the turn ratio. So they ensure that this is true. And then they also ensure that the currents also stay in the same ratio, or I should say in the opposite ratio. So then I2 over I1 will be N1 over N2. It's the reciprocal of that first ratio. This is just by definition, engineers have measured these properties. This is what these transformers do to circuits. This is the first principle definitions of what these transformers do. They ensure that these ratios are true. So now, what does this mean for us? Well, let's go ahead and just rearrange this bottom equation to say that, we could say that, or let's actually not rearrange it at all. We just want to say that I2 is V2 minus 0 all over Z2, but let's substitute in what we know for I2. So we know that I2 is actually going to be equal to N1 all over N2 times I1. So let's go ahead and plug that in for I2 over here. So I2 is actually going to be N1 all over N2 times I1. And then for V2, let's substitute in what we know is true for V2, which is going to be N2 all over N1 times V1. Boom. So let's go ahead and plug that in for V2. It's going to be N2 all over N1 times V1. And then what can we do over there? Well, let's, what we're going to do just some rearranging over here. I'm going to multiply both sides by N2 all over N1. I'm going to multiply this side by N2 over N1 as well. And then I'm going to get this equation, which is I1 equals N2 squared all over N1 squared times V1. And then this 0 is not affected at all. Still, it's just 0 divided by Z2. And then finally, let's go ahead and just make one more change here, which let's just say that I1 is equal to V1 minus 0 all over N1 all over N2, both of those get squared, times Z2. And you'll notice, I know that we're sort of playing fast and loose with the 0 over here. Just convince yourself that these two things are equivalent, because I can just flip this, take the reciprocal of this and put this factor into the denominator. And of course, I'm basically factoring that out of the 0, but that doesn't really matter. And but down here, you can now see that we also have this relationship between I1 and V1. We originally had this relationship between I1 and V1. We said I1 was equal to the voltage difference here divided by this impedance. But we also have that I1 is the voltage difference from V1 minus 0, which is V1 minus ground, divided by this special impedance here, which is Z2 times this squared factor, which happens to be N1 squared over N2 squared. So it's almost like we can just replace this transformer with some sort of new impedance, and we can just get rid of this whole side of the circuit here, and we can just replace this transformer with something that has a complex impedance of, and let me just make that a little bigger so I can include everything. I now want something with a complex impedance of N1 squared all over N2 squared times Z2. So I can get rid of that transformer and just bring that impedance over here, scale it by this special factor, N1 squared over N2 squared, and pull it into this side of the circuit. So that's how you can always rederive this special formula. But in general, you just have to remember this formula here, where you can get this special Z prime, this equivalent impedance, by taking N1 squared all over N2 squared times Z2. And now you know how to derive that. So let's go ahead and apply those same rules here. So what is the impedance on this side of the circuit? Well, I see that these two impedances are in parallel, so that means they can add together to be some equivalent impedance, which is going to be their sum, 2J plus 2. But now, now that we know that there's an impedance of, let me just redraw that so it's perfectly clear. We know that we have this impedance of 2J plus 2 on this side of the circuit. Now I want to bring it through the transformers and plug it into that side of the circuit. So let's go ahead and do that. We can just get rid of all that. And I'm going to plug it into this side of the circuit such that I have this new thing. And it's going to be the same impedance, 2J plus 2, but I have to remember to multiply by that special squared factor, which is N1 squared all over n2 squared. And you recall that we said n2 all over n1 was equal to 2. So that means that n2 over n1 was equal to 2. So now we know that n1 squared over n2 squared must be equal to 1/4, because it's just going to be the reciprocal of this squared. So I need to multiply this by that extra 1/4 factor. And now we're just going to solve for the voltage here. I don't know what we want to call that. Let's just call that V1. And then once we have V1, we can sort of unpackage this and find the actual voltage of interest, which was in the other branch of the circuit. So I'm just going to redraw this whole thing up here. And we're just gonna go through it now that we've simplified this circuit. So our forcing function over here was negative J. We had this resistor of 1. We had this capacitor, which was 1 over 2J. We had this voltage V1 which now we're looking to find. And then we have this new complex impedance, which is 1/4 times, I think it's 2J plus 2. Am I correct? Yeah. 2J plus 2. Perfect. Okay. So how can we go about finding V1? Well, actually, let's just use the voltage divider rules, which tell us that V1 is going to equal the voltage down here, which is 1/4 times 2J plus 2, divided by that same voltage, 1/4 times 2J plus 2, plus, not that same voltage, that same impedance, plus the impedance up here, which is 1 plus 1 over 2J. And these are in series, so I just am getting the total impedance of this branch by adding them together. And then I, of course, then have to multiply by the forcing function over here at the very end. This is just the voltage divider formula, V1 is going to equal the impedance here, Z2 all over Z2 plus Z1 times the total voltage, V total. I'm just using that classic voltage divider formula. So just want to make sure you know where that's coming from. So now let's go ahead and simplify this whole formula here. So we know that V1, let me just distribute this 1/4. That's going to give me 1/2 J plus 1/2 all over 1/2 J plus 1/2 plus 1 plus, and if I bring this J, which is in the denominator of this tiny fraction, into the numerator, remember that makes me flip signs. I have to add a negative there. That's just a rule of complex, the imaginary unit. We know that 1 over J equals negative J. You can look that up online. That's just by definition. So I'm going to flip this J into the numerator here, and then I got to add the negative, which is negative 1/2 J. And then now what happens? Oh, now nice. I can cancel these. And this is actually working out really nice. Oh, and don't let me forget this factor of negative J over there. Now I can just have a nice real denominator, which is going to be, it's just going to be 1 plus 1/2, which is 3/2 in the denominator, times negative J. And then let me just go ahead and keep simplifying this a little bit. So I know that this voltage, let me just flip this 3/2 into the numerator and make that 2/3. And then let me also just distribute this negative J. I'm going to get 1/2 times negative J, and that's going to be squared there because I got 2 of those J's. And I know that negative J squared is going to be positive 1, right? Because that's just by definition. j squared is -1, and then this extra negative makes it just +1. So that whole thing just goes away to 1. And then I also distribute it to this term, right? The second term, and I'm left with -1/2 j, all very nice. And then let me just distribute this 2/3 into here, into both of those terms. And so then I'm just going to end up with 1/3 minus 1/3 j. Okay, perfect. Now I've got my final answer for that impedance, or for that voltage right there at that node. And now I'd like to convert that into the, back from the phasor domain, where this is a complex number, back into the time domain. So remembering the way I do this, we've done this in previous videos, we now want to go from this all the way back to this domain. So I need to find the modulus of this complex number first. So what is the modulus of this? Well, I take the real part, square it, and then I take the imaginary part, which is -1/3, square it, add those together, and take the square root. So this is how I find the modulus of this complex number. So what is that going to be? Well, that's going to be the square root of 1/3 squared. That's going to be 1/9, and this is going to be 1/9. And so if I add those together, that's going to give me the square root of 2/9, or that's going to give me √2/3. So that's the modulus of V1 is √2/3. So I got to remember that. That's going to go into that time domain answer. And then let's also think about how we find the phase of V1. So we're going to take the imaginary component. Remember that we have to take the arctangent of the imaginary component, which is going to be -1/3. And we're going to divide that by the real component, which is +1/3, which gives me arctangent of -1, which is going to give me, that's arctangent of -1. I actually don't need to write this again. I know that this is going to give me -π4. And you can also check to make sure that we're in the right quadrant of the unit circle, because my imaginary part is negative, so we're in this bottom half of the circle, and my real part is +1/3, which means we're in this half of the circle, and that means we gotta be in this lower quadrant where there's two shaded areas intersect. And we got +1/3 here, -1/3 here. That means our answer angle right here is going to be -π4. So that's all, that's all kosher. It's all good. If we had to do something out, we had our angle in a different quadrant over here, we might have had to compensate by adding, an extra factor or adding an extra term of pi or something like that. But it was all in this fourth quadrant here, which is all good. It's all harmonized. We're not in any of these weird quadrants on the left. So all good. And so now we know that the phase of V1, let's say phi, is equal to -π4. And so let's go ahead and then we know this amplitude and phase. Let's reverse that and put it into this equation right here, and get our time domain signal. So then, therefore, I know that V1 is then going to equal √2/3 times cosine of, let's keep that original forcing function, 2t, minus π4. I also think earlier, I think my original forcing function was in terms of sine. So I'd actually like this sort of final answer to be in terms of sine. And recall that I think I already wrote this earlier, but I wrote that, I think I wrote this on the other board, that cosine of some angle is going to be equal to sine plus pi halves of some angle. So I can, I think that's backwards. Sorry, it's sine, I think it's, actually, see, this is the problem. I try to memorize it, but you really just have to rederive it every time. I find that I can never memorize this. You really just have to rederive it by looking on this graph here. So I have the cosine function here, I have the sine function here, and I would like to write, let's say I have a cosine, but I'd like to write cosine in terms of sine. So I know that I have this sine function here, and how can I get this sine function to be a cosine function? Well, I'm gonna have to shift it left by a quarter of a period. So that's gonna be that cosine of theta is equal to sine of theta plus pi halves, because shifting left is counterintuitive, right? So shifting is counterintuitive. So a negative shift corresponds to a plus here. So now let me just go ahead and apply this shift formula to this. So then I know that V1 is actually root 2 over 3. And now I can turn the cosine into a sine by just adding pi halves to this original argument. So it's actually going to be sine of 2t minus pi fourths plus pi halves, right? I take this argument, copy and paste it there, and then add on this extra pi halves. And so that just then collapses into positive pi fourths, right? I'm just combining those angles. Negative pi fourths plus pi halves is positive pi fourths. Okay, perfect. So I found V1, the time domain signal, at this node right here. But for the final step, we remember that that was not our final goal. Our final goal was actually to find V2, which was going to be on this side of the transformer. And then we had some other impedance over here, which was some inductor plus some resistor, etc. So we have V1, but our final goal was actually to find V2. But finding V2 from V1 is so simple because we know that V2 over V1 has to share that N2 all over N1 ratio. That's by definition. So, and we know that N2 over N1 was actually just 2. So all we need to do is multiply V1 by 2 to find the voltage above this part of the transformer. So our final answer for this whole problem is going to be V2 is equal to that extra factor of 2 times root 2 all over 3 times sine of 2t plus pi fourths. And of course, we always work in radians right there.